So now that we know the form that physical laws should take in order for them to be compatible with special relativity, we can go back to two sets of laws that we're familiar with, Newton's laws and Maxwell's equations. And we can look for their compatibility with special relativity. Now, as we discussed at the very beginning of these lectures, Newton's laws are going to be incompatible with special relativity because in Newton's framework, time is absolute and the speed of light is not constant to all inertial observers. Okay, that is, Newton's laws obey Galilean relativity rather than special relativity. So if we look at Newton's second law, so Newton's second law tells us that force is mass times acceleration. Now, under rotations, we would easily see that the force would transform to some rotated force vector, and the acceleration would transform to some rotated acceleration vector. So the laws preserve their same form under rotations. Okay. However, under Lorentz transformation, what we would need is for the law to retain its same form is that the dictionary should tell us that the force transforms to some f prime and the acceleration transforms to some a prime. Let's assume m is the rest mass, so it doesn't transform, in such a way that that the form of the equation is preserved. But as we've just discussed, the only way to preserve the form of the equation under Lorentz transformations is if the quantity on the left-hand side of the equation and the quantity on the right-hand side of the equation transform as tensors of the same rank. So the first thing we want is left-hand side and right-hand side should transform as tensors of the same rank under Lorentz transformations. The second thing is, we know Newton's laws are a good approximation, at least for speeds much smaller than the speed of light. Okay, so in the limit where we make a transformation where the speed is much smaller than the speed of light, or the speed of objects that we're looking at is much smaller than the speed of light, then the law should take the form f is ma. Okay, in that limit. So this gives us an idea for how we can possibly generalize Newton's laws so that they are compatible with the transformations of special relativity. Okay, and to do that, the simple idea is, instead of looking at three vectors, that is, things that transform under rotations, let's look at four vectors. So what we're looking for now is a generalization of the left-hand side and the right-hand side of Newton's laws. So something of this form. Okay, we need a four-vector f mu, and we want to set this equal to mass times acceleration. Okay, where this is the acceleration four-vector. And this is some generalized force, which is a four-vector force. Okay, we don't quite know what this four-vector force is, Okay, but we can guess that the form of the law should take some form like this. Okay, so this is a guess for the form of the law. And another important point is, since we want the right-hand side to transform like a 4 vector, this quantity m should be Lorentz invariant. So a natural choice for the mass would be the rest mass of a particle. Okay, the particle which is experiencing these forces. Now, let's, so rather than try to study this more complicated law, let's study this law in a particular limit where the external forces are 0. Okay, that is, imagine a system where I have no external forces, or let's just take a single particle on which we have no external forces, and let's ask what Newton's laws imply. Okay, so this generalized Newton's law would imply that the mass times acceleration of such a particle would be 0, mass times 4 acceleration. Okay, so when we say 0, of course what we mean is for each component of the acceleration, the 4 acceleration, it's 0. Now we can recall what the definition of 4 acceleration is. The 4 acceleration is the derivative of the 4 velocity with respect to the proper time of the particle. Okay, which we can write in a slightly different way. We can write it like this. Okay, and this quantity, we can think of it, this is mass times 4 velocity. And this is a natural candidate for what we would call 4 momentum. Okay, so just like we define 3 momentum as mass times 3 velocity, we define 4 momentum as rest mass times 4 velocity. So this is what we call 4 momentum. And what we see is Newton's law, this generalized guess for Newton's laws would tell us that dp mu d tau is 0. Okay, so if we solve this equation, it tells us that the 4 momentum is constant or is conserved. Okay, and the important point is that the form of this law is the same in any reference frame. So I wrote this law down in a reference frame S, but if we were to write this law down in a reference frame S prime, we would simply write down dp prime mu d tau is 0 in the reference frame S prime. Tau is the same no matter which frame you calculate it in, because it's just proper time of the particle. And p mu transforms like a 4 vector. So the law preserves the same form in any reference frames. Okay. And so what this is telling us is that in any reference frame, okay, the 4 momentum p mu is conserved. Okay, so this would be true in frame S, but it would also be true in a different reference frame S prime. So in the absence of forces, force momentum is conserved. Okay, so let's explore this a little more. Let's ask, what is this quantity p mu, and what are these 4 things that are conserved? So p mu is m times u mu, and let's write down explicitly each of these components. So if you recall the components of the 4 velocity, it's mc over the square root of 1 minus u square by c square, where the particle has a velocity u in the frame S, and whose components are ux, uy, and uz. So this is what we mean by the momentum 4 vector. Okay, these are the components of the momentum 4 vector. So what Newton's second law is telling us is, in the absence of forces, each of these quantities is conserved in the absence of external forces. Okay, so let's try to understand now what each of these components are. Okay, so and this would be true, remember, in any reference frame, whether you're in a frame S or in a frame S prime, all of these 4 quantities would be conserved. Of course, ux, uy, and uz would change as I go from one reference frame to another. Okay, so now let's look, for example, at the x component of momentum, of 4 momentum. This is mux over square root of 1 minus u square by c square. This is conserved. Now, what you see is, in the limit that u is much less than c, px is approximately m times ux. Okay, so we recover Newton's laws for standard 3 momentum conservation in the absence of external forces. When the speeds of particles are, so the speed is u, when the speed is much less than the speed of light. Okay, so we've got a generalization of Newton's laws which seems to give us the right physical effect in the limit that the speed is much less than the speed of light. Okay, and this would similarly be true for py and pz as well. Okay, in the limit u much less than z, py would just be m times uy, pz would be m times uz. Okay, now we could ask, well, what about this new thing? Okay, so previously we had 3 vectors, now we have 4 vectors. So what is this quantity over here? Okay, so in other words, what is p0? So p0 is m times c over the square root of 1 minus u square by c square. Okay, and it'll actually be useful to think about p0 times c rather than p0 itself. So let's think of p0 times c. This is mc square over the square root of 1 minus u square by c square. Now, this quantity, the claim is that this is conserved, right? The generalized Newton's law would tell us that this is conserved in the absence of external forces. External 4 forces. Okay, 4 vector forces. So now let's ask, well, what is this quantity? Maybe we can gain some intuition, okay, by asking what is this in the limit that u is much less than c. So p0c would just be mc square in that limit. All right. However, we could do better by going to next order in u. Okay, so we would use the binomial expansion of this denominator, and we can write this as 1 plus half u square by c square. And at next order, we would have things like plus minus half minus 3 by 2 u to the 4 over c to the 4 by 2 factorial, and so on. So we can now write this as mc square plus half m times u square plus 3 by 8 m0 or m u to the 4 over c squared, and so on. Okay, and if you look at this first leading order correction, okay, to P0c just being mc square, this just looks like your kinetic energy in Newton's theory. And in the absence of external forces, or in the absence of a potential energy, the kinetic energy is the total energy of a particle. Okay, so a natural guess for what this quantity P0c is that this might be the right expression for what we should call energy of the system. So the energy of a particle in the absence of external forces is mc square plus half mu square plus 3 by 8 mu to the 4 by c square plus so on. This is the energy of a particle in the absence of external forces. Okay, so what is kinetic energy? Kinetic energy is just the energy possessed by a particle due to its momentum or due to its velocity. Okay, so the fact that the particle has a velocity gives rise to some energy. But what we see is that even if the particle's energy was 0, the particle would still have some energy. Okay, so even for a particle of 0 velocity in some reference frame, in frame S, it would have an energy which would be mc square. Okay, so this is the most famous equation in the history of physics. E is equal to mc square. Okay, so this is called rest mass energy. And what this equation is really telling us is that mass or rest mass, the fact that particles just possess mass, is an indication that they have energy. Okay, so normally we could always add any constant to the total energy and not worry about it. Okay, because as long as this energy is locked up inside the particle, it doesn't matter. However, the fact that this, if we look at the exact expression for energy, which is P0 times C, this is m times c square over the square root of 1 minus u square by c square. So it's only in the limit where the speed is much less than c is that where we think of the rest mass energy as being something completely distinct from the kinetic energy of the particle. However, when you look at this expression, you see that the rest mass energy is just a very particular limit of the energy of a particle. It's the energy in when the particle has 0 velocity in a particular reference frame. Now, if there was some way to unlock this energy, okay, that is, you could convert this particle from one form to another, let's say through a radioactive decay or some kind of collision process, then it would be possible to transfer that rest mass energy into other forms of energy. So previously in Newton's laws, we had a separate rule assuming conservation of mass. Okay, this was just an assumed thing. And in the absence of external forces or an external potential, we also had conservation of energy. Now we find in special relativity, the only thing that's conserved is this quantity, P0 times C, in the absence of external forces. And this quantity is what we call energy or mass energy. Okay, it's a combination of mass energy and kinetic energy. And so there's only one rule. Okay, so in special relativity, the generalization of Newton's laws tells us that there is only one conserved quantity for mass or energy, and that is a generalized conservation of mass energy. Okay, or sometimes this is just called energy. And in the limit that the speeds are much smaller than the speed of light, there is a separate conservation of mass and a separate conservation of kinetic energy. Okay, and of course we're neglecting corrections which are suppressed relative to the original kinetic energy by order of u squared by c squared. So as long as the speeds are much smaller than the speed of light, these extra corrections are small and we ignore them as we do with Newton's laws. Okay, so we'll explore some implications of the conservation of this mass energy in a moment. But before we do that, let's just ask another question, which is, now that I have this 4 vector P mu, we can construct a Lorentz invariant quantity by constructing the dot product of P mu with itself. Okay, that is, we can construct the quantity P mu, which should be Lorentz invariant. And this quantity, where this is a covariant 4 vector and this is the contravariant 4 vector, or I can write this using the metric G mu nu as G mu nu P nu, or I can write it as, in matrix notation, P transpose dot G dot P. Okay, all of this is 4 vector dot product. And this quantity is going to be equal to, so if you remember P mu now, P mu, we interpreted the components as some generalized energy, okay, some generalized momentum. So these were the components of P mu. And so now what we're going to get for this dot product will be E square by C square minus Px square minus Py square minus Pz square. And if we plug in expressions now for E, which was mc square over the square root of 1 minus u square by c square, and for Px, which is mux over the square root of 1 minus u square by c square, and so on for Py and Pz, then what you would find is that this dot product would just give you m so it would be m times c, okay, which is Lorentz invariant. So the 4 vector dot product of momentum just gives us a Lorentz invariant quantity. And in fact, this is how you would infer the mass of a particle, is in different reference frames, each observer would measure different momenta. And if they calculated, if each observer calculated in their reference frame what this 4 vector dot product is, they would get the same answer. And they interpret the quantity that they get as the mass of the particle times c, or the rest mass of the particle. This is just like how when different observers want to calculate proper time, they would use the distance between two space-time points calculated in their own reference frame, and the result would just be proper time, okay, of a particular clock, where the space-time interval is calculated between two space-time points which are measuring the proper time of this clock in its rest frame. Okay, so you can use the form momentum to actually infer the rest mass of the particle if you're in a reference frame which is not at rest with the particle. And now if we write this out explicitly, okay, so the relation that we found is that E square over C square is E square by C square minus Px square minus Py square minus Pz square is, sorry, I made a mistake here. This is m times C the whole square. Okay, so this is m times C the whole square. So if we simplify this equation, we can write this as E square is vector P square plus P square times C square plus M square C to the 4. Where the vector P is the components of this generalized form momentum. So that is, if I take Px, okay, that would be m times ux over the square root of 1 minus u squared by c squared, and so on for py and pz. Okay, so these are the components of what we call vector p. And if we and the mod of vector p square is just px square plus py square plus pz square. Okay, so this is our generalized relation between energy, momentum, and mass. Or we can write this as E is equal to square root of mod P. So I'm just going to drop the vector sign, but mod P is the mod of this vector. Mod P square C square plus M square C to the 4. And again, we can expand this for u much less than the speed of light. So for u much less than the speed of light, what that tells us is that P, or any component of P, or mod P, is much, much smaller than mass times C. Okay, so treating this as a very large term and this is a very small term, we can now expand this. So you can show again via the binomial expansion that this is mc square plus, we can write out corrections to this now, plus p square by 2m minus 1/8 p to the 4 by m cubed c square, and so on. Okay, so once again we see that their energy is rest mass energy plus conventional kinetic energy of Newton, and you have higher order corrections now.